This video is going to be all about vectors. Now, much of what we study in this video may be um, it may be review for you, especially if you took Math 142 at YBC. We study vectors in there. Um, but there will be some new stuff in here, so don't shut the video off now. But I will start from the beginning because I'm not going to assume that everyone has the same experience with vectors. So we will start from square one here with just kind of what a vector actually is. So here's the definition. It says a vector in the plane is a line segment with an assigned direction. So in the picture below, we have a line segment going from A to B, and you can see it goes in that direction because of the arrow here. Where we call A the initial point and B the terminal point. Now, there's a couple ways to express this vector. On the one hand, we can say that it's AB with a little arrow, so that tells me it's an arrow going from A to B. But more typically, what we'll do is we'll just use this bolded lowercase letter notation. So the textbook and my notes will always use bold lowercase letters to indicate that we're talking about a vector. Now, the only thing about that is when it comes to me writing that out, and when it comes to you writing that out, it's kind of a pain to try to, force what you're writing to be bolded, so what are you going to do? Just kind of color in, and so that's not ideal. So what we want to do is instead of that, what we're going to do is just say our notation will be U, and we'll put a little arrow over it to indicate that it is in fact a vector. All right, so there's lots of contexts that vectors come up in. So just kind of give you some ideas to how to think of this. Suppose that this vector here, the U vector, represents the magnitude and direction of the force that I was applying to some sort of a car, okay? And then all of a sudden I've begun to push twice as hard, okay? So I'm applying this force in this direction to a vehicle that I'm trying to push down the street. So if I begin to push twice as hard, then we would represent that by just doubling the length of our vector. Let me put a little 2 in front of the original vector 2 to indicate we've doubled the length. Now if then instead I grab the bumper and then attempted to pull the vehicle the other direction with the same force, then I would say it's negative U because it's the same length, but it's in the opposite direction. All right, so what I want to do is talk about how do we add vectors, and at first we're not even going to talk about it algebraically. We're just going to talk about it in pictures. Okay, so to kind of give some context here, I want you to think, in this case, of U as the speed and direction of an airplane relative to the air. So if it was in completely still air, what's the speed and direction of the airplane? And then this other vector is going to represent the speed and direction of the wind. All right, and so of course the speed and direction of wind is going to be a lot less, the speed of the wind is a lot less than the speed of the airplane, so it makes sense that it's a much shorter vector. So if we're talking about adding the two vectors together, the way we do that is you attach the end of V to, the beginning of V to the end of U, just like in this picture. So we had our U, I attached the beginning of V to the end of U, and then wherever that ends up, if I draw a line from where I started to where I end, that's the vector U plus V, okay? And the way we would interpret U plus V in this little situation we've set up is that it is the actual speed and direction of the plane, okay? Because we have some of the wind heading in the same direction the plane was anyway, so it makes sense that the plane's going a little faster, but it also knocks it off course a little bit, so it's also going to change the direction that the plane is actually going. All right, so when we work with vectors, we need to be able to write them down in what's called their component form. Okay, and their component form is literally just telling us how far over and how far up or down do we go. Okay, so it's a lot like the idea of an ordered pair. Okay, so if I have a vector like in this picture here, where if I started it from the origin, I would go over x and up y to get to the terminal point, then I would call this vector x comma y with these angled brackets, right? And so we want to use the angled brackets to be able to distinguish it from the idea of just the point x comma y, right? So this is this arrow here, whereas if I was talking about just the point xy, then I would be using just parentheses x comma y. All right, and then we can also talk about vectors in three-dimensional space, right? We're moving into that now. So then we would just say that a vector, and this, sorry, there should be a little equal sign here, not, there we go. Let's maybe squeeze it in there. Then we would just say x comma y comma z. So there's an x component, a y component, and a z component. All right, so let's talk about actually adding vectors algebraically. So I've expressed the way to do that algebraically in both 2 dimensions and 3 dimensions, right? But all you're going to do is just add the components together. So let's, what it wants us to do is sketch u, sketch v, then sketch u plus v. So I can sketch u, and I'm going to sketch it just starting at the origin, and then I'm going to go over 2, up 5. Okay, so there's my u. And then my v is going to go over 3, down 2 from the origin. Here's my v. All right, so then u plus v. Well, first let's do it algebraically. U plus v is going to equal 2 plus 3, the 2x components, and then comma 5 plus negative 2, which is 5, 3. All right, so what that should mean is that if I go over 5, up 3, that is u plus v. Now let's take what we learned at the beginning about how to show vector addition geometrically, and let's make sure that it bears out here. So I'm going to put u first. Okay, so u is, remember, over 2, up 5, so that goes up there. All right, and then let's use a different color here. So for v then, we know we're supposed to go over 3, down 2. So you can see this at work, right? What we showed on that previous page, that if I attach the beginning of v to the end of u, that will lead me to the picture for u plus v. All right. Now, we can also do what's called scalar multiplication. So that just means we're going to multiply our vector by some constant number c. And then the way that that actually gets carried out is you then multiply each of the components by that number c. So here you can see we have c times the vector u equals c times x in the x component and c times y in the y component, and then similarly for 3 dimensions. So example 2 wants us to kind of put all this together. So they want us to say what is 2a minus 7b. So that's 2 times negative 2, 3, 5 minus 7 times 1, 0, negative 2. And then I distribute that 2 essentially through to each component, so it's negative 4, 6, 10 minus 7, 0, negative 14. So then I'm just going to take negative 4 minus 7, 6 minus 0, and 10 minus negative 14. which is negative 11, 6, 24. Right? So we can do more complex arithmetic that involves both scalar multiplication and addition and subtraction, right? And it works pretty much the way you would expect it should work. All right, now at this point I want to address what may or may not be a question for you, which is, okay, what is the real difference between when we talk about the point 3, 2 versus the vector 3, 2, right? Do we really understand what the difference is? Okay, so the way that I would answer that is down here, every single one of these vectors is the vector 3, 2. So in other words, while we give this vector the name 3, 2, because if I were to start it at the origin, you would go over 3 in your x and up 2 in your y. The starting place doesn't matter. So you have all these other vectors that I've drawn in here that end in different places, but they're still the vector 3, 2. And of course, what's happening, let's just take this one for instance. Its terminal point is 4. The terminal point of its x is 4, and then the initial is 1. So if you take 4 minus 1, and then you take 5 minus 3, of course you actually get 3, 2, right? So basically vectors are mobile, right? They're not stuck in one place. The point 3, 2 is just a point in one spot. A vector can move all over the place and it's still the same vector. All right, and the same thing I can emphasize in 3 dimensions, right? So here's a vector in 3 dimensions, a1, a2, a3, but this is the same vector that goes from the point x, y, z to the point x plus a1, y plus a2, z plus a3. It's the same exact vector, and if I were to take this minus this, I of course get a1 again, right? So this, if there's one thing that I think will really help you in the coming sections, it's this idea that vectors are mobile, right? And it doesn't change what the vector is when you talk about moving that vector around. All right, now it's also worth pointing out that vector arithmetic has various properties that are very similar to the properties you're familiar with numbers. So number 1 just says that I can add vectors in either order and get the same answer. Number 2 is the associative property that says if you have a group of 3 vectors to add, you can add the first 2 first or the second 2 first. It doesn't matter. Number 3, there is such thing as a zero vector. And so if you were in 2 dimensions, just understand that the zero vector that we're talking about would be 0, comma 0. Okay? Or if we're in 3 dimensions, the zero vector is 0, comma 0, comma 0. Okay? So we do have that. And then there's also this idea that for every vector, there's an opposite of that vector, so that if you add them, you get the zero vector. You can distribute scalars through to 2 vectors added. You can distribute a vector through to 2 scalars added. And then the associative property of scalar multiplication works. And of course, if you multiply a vector by the scalar 1, you get it back. So here's, these are not worth going through line by line and like saying, okay, let me make flashcards of these. This is just to say that when it comes to addition and scalar multiplication, all the properties that seem like they should be true, because they used to be true for, or they used to be, because they are true for numbers, hold true for vectors as well. All right, so in here, now let's talk about the magnitude. A little bit of a typo here that I'm just now noticing. All of a sudden I switched to V. Okay, I didn't mean to do that, so this should say A right there, so you can make that little fix. So the magnitude or length of a vector A denoted as this, or you might see double bars around the A, and is given by the following formulas. So it's just literally the Pythagorean theorem, right? So if you have a vector and you go over A1 up A2, if you want to know how long this thing is, then just do the Pythagorean theorem. A squared plus b squared equals c squared. So that's all that we're talking about here. So you take the square root to get the magnitude, and then it's the same thing in 3 dimensions. Now, one of the things that we are going to care about when it comes to vectors is having a unit vector. So a vector that has a unit length, or a length of 1. So just know that anytime you want to make a unit vector out of any vector that you are already working with, you can just simply divide it by its magnitude. Okay, so take the vector you're interested in, divide it by its own magnitude, and of course then the resulting vector here has a length of 1. And there are 2 unit vectors that are going to be quite important to us when it comes to 2 dimensions, and that is the vector I, which is 1, 0, and the vector j, which is 0, 1. So, and you can see down here, right, and you can see why they're nice and convenient. These are called the standard basis vectors, and those of you who've taken linear algebra, that is a very familiar term to you. All right, so what we can do with these is write any vector in terms of I and j. So this little bold I and bold j, by the way, when I write it on paper to indicate that it's a unit vector, what I will often do is I'll do that instead. So instead of the arrow on top of the I and on top of the j, you'll see me write this. And that's kind of convention for how to express I, j, and then, as you'll see later, k as well. All right, so what we can do is if we have a vector that's got components a1 and a2, then what we can do is just take a1 times I plus a2 times j. And the way that works is, you can always separate a1, a2 like this, and then you can pull out a scalar a1 and a2 from here, and then you have 1, 0, and 0, 1, which are I and j. So you need to be comfortable with that notation as well. And then, of course, the same idea applies to 3-dimension, and so we just add a k, and boy, I guess I'm just full of typos in this particular set of notes. So I guess right here forgot my equal sign, so sorry about that. So it should say k equals, of course, 0, 0, 1. All right, so any vector in R3 can be written in terms of I, j, and k in this way. And here's what I, j, and k look like in 3 dimensions. All right, so just to do one practice problem with this. Take a look at example 3 here. So what we're going to do is the same type of problem we did earlier, some scalar multiples times vectors added and subtracted. But now we're going to express those in terms of their ij notation. One of the reasons ij notation is so nice is because you can kind of work the problem out kind of thinking in terms of like terms, like you would in algebra class. So what I can do here is say 3 times, and then I would just say 5i plus j minus 2 times 4i minus 7j. And that's going to give me 15i plus 3j minus 8i plus 14j, right? So I'm kind of treating these like they're like x's and y's, right? And then of course we combine our like terms. 15 minus 8 is 7i, and then 3j plus 14j is 17j. So we can do all that vector arithmetic in this new notation. All right. And kind of the last topic I want to address here, and then we'll do a couple of application problems so you can see how to apply these ideas. It says let A be an R2. Okay, so right now we're just sticking to two-dimensional space. And it has a magnitude, of course, of this, right, the magnitude of A, and a direction of theta. So that means it makes an angle of theta with the x-axis, right, from standard position. Because remember, we're always going to measure angles from the positive x-axis. Then what we know is that the x component of this vector is always the magnitude of the vector times the cosine of the angle. And of course, the reason for that is, we know that the cosine of theta is the adjacent over the hypotenuse, right? So, in other words, cosine of theta is A1 over the magnitude of A. So then solving for A1 just gives you that. And similarly, the A2 component, the y component, is the magnitude times the sine of theta. So we can always use that in any situation where it's appropriate. And then the last thing that I forgot to put on here, so definitely make some space for this, is that what we know is that if you divide these two equations by each other, then what you're going to have is that A2 over A1 is equal to this divided by this, right? But of course those magnitudes cancel out, so that means it's equal to the tangent of theta. So we may find the need when we want to figure out a particular angle, we know that that's just going to be the ratio of A2 over A1, or y over x. All right, so let's do a couple of applications here. So in example 6, we have an airplane is pointed due south and flying at 320 miles per hour relative to the air. If a wind is blowing at 20 miles per hour in the direction of 40 degrees west of north, find the true speed and direction of the plane. So first, if you're not familiar with bearings or headings, this means 40 degrees west of due north. So, so the idea here is that you start by pointing north and then you go 40 degrees to the western direction of that. All right, so let's draw out, we have a couple of vectors, right? So we're flying 320 miles per hour relative to the air due south. That's what we're doing right now. That's what the plane is, I guess, trying to do, right? So there's one vector, what the plane's trying to do. But then we have a direction of only 20 miles per hour, so it's going to be a pretty small arrow here, but it's 40 degrees west of north. So I start by pointing myself north, and then I'm going to go west of that. So I have something like this. And this angle right here is 40 degrees. Find the true speed and direction of the airplane. Well, based upon our work earlier with taking just the pictures of vectors and talking about vector addition, I think the idea here is that we know that we've just attached the beginning of one vector to the end of another, so that is vector addition. So the idea here is the result of this wind is that the speed and direction of this plane are actually going to be a little bit different. All right, so maybe let's call this one V and this one W for wind. Then the idea is that the true speed and direction of the plane It's going to be v plus w. All right. So let's go ahead and write these out. So first of all, how do I write out v? Okay. Well, v doesn't go anywhere left and right. So that means it has a 0 x component. But it's going 320 miles per hour south. Okay, now let's go ahead and preserve the idea of our coordinate system that we're used to working with, which would say that if we're going down, that means negative. So I'm going to say negative 320. All right, now let's look at w. Well, remember on the previous page what we learned. If we know the magnitude, right, and we know the angle, then the x and y components are just being given by the magnitude times the cosine and the magnitude times the sine respectively. So what I can do here is I can say this is the magnitude, which I know is 20 miles per hour, right, because that's the speed at which it's blowing, 20 times the cosine of my angle. Okay, but what's my angle? Remember, we always want to measure from the positive x-axis. So be careful, don't put 40 degrees in there. Measure it from here. So if 40 degrees is here, and this is 90, then total, we know that this is going to be 130. All right, so that's the number that we place in for our angle here. And then 20 times the sine of 130. All right, and so we want to add these together. V plus W. So 0 plus this, so 20 times the cosine of 130 degrees. And then negative 320 plus 20 times the sine of 130 degrees. So this is this vector v plus w. But let's think about what it asks for. What is the true speed and direction? Okay, so what's the speed going to be? Well, the speed has got to be the magnitude of v plus w. Right, so I have the square root of 20 cosine of 130 squared plus negative 320 plus 20 sine of 130 degrees squared. So I put that in my calculator, and out comes this number, which does make some sense for us. So 304 point, actually it's going to round to, let's call about 305. 305 miles per hour. Now let's think about what's happening. The plane was trying to go 320 miles per hour, but a significant amount of that wind is fighting it, right? And so you can see that u plus v should be shorter, so that means it should actually be going slower. So there's its true speed. But then of course true direction, right? What did we learn last time? Or on the previous page we said the tangent of theta is the y over the x component. So we can use that here as well. So we can say that the tangent of theta is equal to negative 320 plus the sine of 130 divided by 20 cosine of 130. All right, but then of course we're going to have to use tan inverse. So we know that theta is the tan inverse of this. Okay, now we do have to remember our trig here. It's important for us to check based on what answer this gives us. Okay, so let me change colors here so that this right here, and of course we're going to make sure we're in degree mode, this gives you an angle of 87.6 degrees. Now, clearly that can't be right because 87.6 degrees means starting from here, 87.6 degrees is pointing up in this direction, okay? But remember that tan inverse only gives you things between negative 90 and positive 90. So of course what's happening here is that this actual angle right here is 180 degrees bigger than the number it spits out, okay? So my theta is not, so while theta is not 87.6 degrees, right? It's much larger than that. It's 180 degrees bigger. So I need to add 180 degrees. So what we get here is 267.6 degrees. Okay, but what we really want to do is be able to give an answer like this, right? Some sort of a heading. So what I'm thinking is that the very best way to report this answer is to say, let's start by going due south and say, how far do I got to go this way? Well, due south is 270 degrees, right? So here's how I would answer the question. So 270 degrees minus 267.6 degrees is equal to 2.4 degrees. So my answer is start due south, go 2.4 degrees to the west. All right, let's do one more example, kind of a different flavor in this second one. All right, so we have two tugboats are towing a large ship due east into port. The larger tug exerts a force of 4,000 pounds on its cable, and the smaller tug exerts a force of 3,200 pounds on its cable. The smaller tug is pointed in the direction 60 degrees east of due south. In what direction must the larger boat be pointed so that the ship will be heading exactly due east into port? All right, so in this picture, what we want to do is we kind of want to draw not only the vectors that they're referring to here, but also the one that they're wanting, right? So I'm going to think of it like this. So here's my kind of an imaginary north-south line. I know that what I want is a vector that goes directly due to the east. And I know that I've already got one that's going 60 degrees east of south. So that's going to be something like this, or that's 60 degrees. So then the idea here is, okay, and we know that this one is, and we'll call this one, let's call this one U. So we know that the magnitude of U is equal to 3,200 pounds. So the idea here is that I want another vector, and I know, we'll call this one V. I know that this V has a magnitude of 4,000 pounds, but I don't know what direction it's pointing in. But what I do know is that when I add this to this, I need to get this. Okay, but you can kind of imagine, right? Me taking this vector and putting it here, right? The vector addition would work. And so the question is, what should this angle be in order to make it work? All right, so we know that U is 3,200 times the cosine of, and let's be careful, we got to give this actual angle here, right? So that actual angle is not 30 degrees, it's negative 30 degrees, right? Because we're going in the clockwise direction. And then 3,200 pounds times the sine of negative 30 degrees. And then V has the unknown theta in it, right? So I do know that it's going to be 4,000 times the cosine, oops, mistake there, times the cosine of theta, 4,000 times the sine of theta. And then we know that this vector that we're trying to make, this is u plus v, right? Which is, of course, 3200 cosine of negative 30 degrees plus, and ooh, I need more space than that, sorry. Let's start over there. So it'll be u plus v, so 3200 cosine of negative 30 degrees plus 4000 times the cosine of theta, and then 3200 sine negative 30 degrees plus 4000 times the sine of theta. Okay, so now let's think about this. What do we know about this thing? The thing we know about this vector we're trying to create is that the y component should be 0, right? This is equal to 0. And that's what allows me to solve this problem and figure out what theta should be. So I can say 3200 times the sine of negative 30 degrees plus 400, or 4000, excuse me, sine theta has to equal 0. And by the way, sine of negative 30 degrees is negative a half, so this whole thing turns into negative 1600 plus 4000 sine theta. So 4000 sine theta is equal to 1600. Okay, and so then theta, of course, is going to be the sine inverse of this, which gives me 23.6 degrees. Now just remember, you've got to make that some sort of a heading or a bearing. So I could say something like start due east and go 23.6 degrees to the north, right? Start due east and go 23.6 degrees to the north. Or you could subtract that from 90 and say, let's start north and go 66.4 degrees to the east. Either way would work.